Right. Okay, we're back. So I was just reading through my book. If you're looking at page 362, you'll see the median cut algorithm and the computation of the signal-to-noise ratio. And what you'll see suggested is that there is a way to implement the median cut algorithm using a recursive algorithm, queuing two different child arrays after a split. The split is very close to what I was doing before, where you were getting the first half and then the second half, and then queuing these two. And then I intimate in my book that this is terribly inefficient because if you do this in color, it results in too many cubes. But having said that, and I can tell you this, you're not doing it in color, and therefore you won't have too many cubes. Moreover, you will have properly implemented a recursive mechanism for implementing the median cut algorithm. That's remarkable. Moreover, we have the histogram already, so we have a mechanism for clearly identifying what the cubes should be. And the cubes are going to be one-dimensional cubes, so we're really dealing with a series of ranges. And each range is going to have a minimum and a maximum. And in fact, instead of, if I were to follow my own algorithm here, only make a small modification, it would be that we're getting a series of ranges. And we could make something called, I don't know if we want to call it a cube, but we'll just call it a range since it's a one-dimensional cube. So let's call it a range. I think that's a very nice idea. The range class consists of a minimum value and a maximum value for each one of the ranges. So we can do something like this. Integer, we want to do integers? I guess we could do shorts. Why not? We have shorts that range from 0 to 355. So let's do it with shorts. I think that's very fine. Doesn't really matter. Does it matter? We'll keep it shorts. Short min equals 0. Short max equals 0. And the range has a short for the min and a short for the max. And what it does is it says this dot min equals min, this dot max equals max, and I think these things should be private, but they should have constructors for doing setters and getters. So there should be a way to encapsulate these things as part of the refactoring. Encapsulate fields, min and max, getter and setter, refactor. And we'll make the constructor public, and that identifies our ranges. And our goal is to get a set of ranges, right? And each time we do these ranges, we're going to enqueue the left side and the right side, or what I call the first half and second half of the queue, and we're going to keep let's see, how many cubes do we need? 256, right? So we're going to have 256 different ranges in an array. Now that I think about it, This might be overly complicated. It says here, reading my book, there are several techniques available for reducing the number of colors in an image or image sequence. One of the more popular algorithms is the median cut algorithm. The basic idea is that the color histogram of the image is computed in RGB color space. But in fact, we're computing the histogram of the image directly in the one-dimensional space that is the values of the pixels. The histogram is then clustered into K groups. So what we're going to do is we're going to take this histogram and we're going to cluster it into 256 groups. Once the clustering is performed, the pixels are mapped to the centroids of the clusters in order to minimize the color error in the image. So what we did here was we got a proper histogram. We got a minimum and a maximum. Where are we here? I'm in the wrong... There's two of them. There it is. But this is histogram from DICOM is what we were doing. So here's the histogram. It looks like there are perhaps there we go. You know, I think would be educational for us is to print out the first 355 elements of the histogram and plot them in Java or Excel. Probably Excel is easy, right? We can just paste it into Excel. So if I did something like that, I could print the histogram using, I think this will do it. Put a print line in here. Oh, look what it did. It just printed the reference number. That's not quite right. Let's put the 10 back in here and get rid of the print line. And then I would like to be able to have a print line in here that works properly. There. Now that should work. So now if I go print line, I want it to print in one column. See if that works. I just did that really quick, but I just wanted to get some formatting done for myself. It didn't work at all, oddly enough. Print line. Why shouldn't that print a new line? God, that's weird. I'm going to inline the print line invocation. Refactor, inline, keep the method. Now tell me why that wouldn't print a new line. That should print a new line. Yeah, now it's working fine, oddly enough. And I can stop it at number 355 if I want to. So I can just go until 355, because that's my maximum value. There's really a nice way to plot this in Java. But what I'm going to do is I'm just going to paste it into Excel because I'm lazy. Paste. That works. Insert. Chart. Column. 2D column. There you go. There, that sort of looks like a histogram. Now your goal is to cluster this histogram into 255 different values. Right? Because what it says here, the median cutout procedure is applied to subcubes until there are k cubes. And in your case, there's going to be 255 different cubes. The centers of the cubes are used for the k input colors in the color map. Given a color map, each pixel is mapped from the original color to its nearest color neighbor. The mapping is done to minimize a color error metric. The color error metric is central to the proper functioning of such algorithms. One way to implement the median cut algorithm is to use a queue to enable a breadth-first cutting of the subcubes. The idea is that an instance of the cube class has a static member variable that is used to keep track of the total number of cubes. And then I give you the example on page 363. And it's a means of clustering. And that's what you're essentially doing, a kind of one-dimensional clustering. So if you went from 0 to 341 and you wanted to find the median, where would the median be at? Where's the median? Yeah, it's in the middle. So in this particular case, it would be 170. That's your middle. So now you've got to take the 0 to 170, and you have to divide that and to a median, and then you do it again from 170 to 340, whatever that is, 341, and then you keep going. Keep subdividing until you have a total of 256 different possible ranges. Then those ranges are going to have to be used for the buckets, and then the pixels have to map into those buckets, and then you have to decide what the new ranges will be for your 256 colors. So we got the splitting of the arrays. I think I wrote a little program for that. I can put that into my little PowerPoint. We can go back, look again at your median cut algorithm. We want minimum and maximum. We already saw how to do that for any given array. We can also split the array. Let's see now. What else can we do here? Segregate the points into two halves at the median point until the desired number of boxes is generated. Compute the representative for each box by averaging the colors contained in each. So here's how you split the array. And we also have a mechanism for ordering the array, right? And I think you could do that with a sort algorithm. Let me see. Did we do sorting before? I think there's something that we did in one of the DICOM readers. mat1.sort sounds like a good one. Can I sort my pels? I think I can. mat1.sort. I got a way to sort shorts. If you sort the shorts, I think you better put it in a new array. Perhaps we could call it spels. And now, how would you box the array? You know the minimum and the maximum, right? So I would say create a new range based on the minimum and maximum. Then you're going to find the median on pels and split that, right? So the first half and the second half, short spels, I'll call it first half or left half. I'll just say spels1 equals. Now, how do you get the left half of this thing? Didn't we just do that? Get second half, get first half? Where was that at? Under examples, maybe? Array split. Get first half, get second half. I could probably move that into mat1, get first half, get second half, I suppose. If it makes a difference. Or I could leave it in array split, whichever you prefer. I kind of like moving it to mat1, but I won't do that just now. So let's put it into array split dot get first half and array split dot get second half. And we'll put in spels, short spels2 equals array split get second half. Now I'm going to have different mins and different maxes. and that'll give me a different range. So in theory, I can keep going, right? I can do short spels 1, 1, which is equal to an array split and now we're going to do a dot get first half. Do you see the recursive nature of this?
Why would we split it again?
Because we don't have enough ranges yet. We have to keep splitting until we're in until the number of ranges is equal to k, where k is equal to the total number of colors. So in effect, the number of cubes is supposed to be perhaps 256. So this has to be repeated 256 times until you have 256 segments. Huh? Well, no, I'm doing it manually now so that you can see through induction how you would extrapolate this in a recursive manner. You know that if you try and use I don't know, I'll call it proof by induction. You usually start by doing things manually in a series, and then you say, and then by induction, and then you show the general form. And so what I'm doing here is I'm showing you sort of the manual method first, and then I'm giving you what I would call the general idea. See, if you look at, I mean, this goes to the basic question of how it was suggested to do it in the book. If you look at the pseudo Java on page 363, what you see is a cube Q, and then what you're doing is you're n-queuing a child array that it comes about from doing a split, and the split n-queues this twice, and then you keep n-queuing while the number of cubes is less than k. And so when you do that, and I don't know if you're following along in the book, but when you do that, you keep going until you have exactly k cubes. But you see, what you can also do is you can read ahead a little bit, and it says that's for illustration only, because if you know what k is in advance, you can just make an array of cubes. And so that's what I suggested as a way in which to formulate this. It's a question of implementation. Once you have the ranges on all the different subsections, then you are in effect going to be able to decide whether a pixel is in that range, and then each one of those ranges will map to the new colors. So in a sense, what you really need are 256 buckets, each one recursively subdividing from the prior. And I'll call this 1, 2. And that'll be arranged as an array split from spels 2. Now, would you do this manually? That's Kyle's question. And the answer is no, of course not. Only if you were in a classroom setting like this trying to show people the structure of what's going on. Because what you're really doing every time you do this split is you're cutting the number of stuff in the stuff in half. And then the question also becomes, is there a better way to do this, right? Should we do this with a for loop? Should we do it with some global iteration? Should we do it with recursion? The book suggests the recursion is very slow. But then I say, well, who cares? if it gives you an elegant solution. So I would leave that to you. And I would suggest that you would be better off deciding on your own whether you wanted that kind of a solution. I can also show you sort of the histogram implementation that I have here, which is not necessarily suitable for your application, but shows you how it was done. Not histogram, median cut. Where did I do that? It should be in color, right? File, find, in path. I'll tell you exactly where it is. It's in j2d.color. This makes a histogram which is relatively small relative to what I was doing. I think I was doing a histogram of 65,536. This is a smaller histogram. Let's see now. This is a linear cut algorithm which removes the least significant bit and then forms the histogram by taking values and counting. Here's how the linear cut algorithm works. Here you can see he's taking the least significant bit off of the red, the least significant bit off the... Let's see now. Is that right? F8 is 1111 and 8 is just 1000. So he's removing the least significant 3 bits off of red, green, and blue. Not a particularly nice thing to do to a 24-bit image, but that's why he's leaving you with 15 bits. So that's making a 15-bit color image out of a 24-bit image. You know, that's Cootieizing the image, right? That's just nasty to do that to a nice image. But he's doing that because why? Because if you had to make a histogram with a 24-bit image, you would have to have 16 million different elements in your histogram, because 2 to the 24 is 16 million. So by making a 15-bit image, you only need a histogram of 32,768 elements. So if you're starting with a 16-bit image, you shouldn't need to do all of that. In theory. Anyways, you can see how the histogram is created here. That's the RGB histogram and reverse color lookup table. And now here's the median cut algorithm using cubes, where the cubes are in color space. And now we're counting cubes based on a histogram where we do the median cut and then we cut the histogram into a median and we keep making smaller and smaller cubes. So what's wrong with doing it with this algorithm, doing it right here with this? Why not just take this algorithm and use it directly with your grayscale images? We only have one color. And the other thing he does right off the bat is he's chopping the least significant 3 bits off of each color. I mean, that's just nasty. So that's no good for you. And now you can see where he's got the lower and upper elements for each one of the cubes as he tries to narrow down the cube list. And he's doing the same exact thing I was doing before with ranges, only he's doing it with red, green, and blue to get you ranges. And he's doing this thing here called the quick sort. And if you look at how quick sort is implemented, it's with an array of ints. Actually, it's also recursive. It's recursive quicksort. As a matter of fact, the interesting thing about the quicksort algorithm is that it never really creates a new array. All it does is it keeps narrowing down the limits over which the sorting occurs until the thing is sorted, and then it merges upon return. So I wouldn't recommend using this. I mean, it wouldn't give you a nice looking image by the time you were done. But it's certainly an interesting algorithm to look at it from this point of view, because what you're seeing here is you're seeing this idea about these median cubes, and instead of using median cubes, we're using ranges. And the only thing we have to care about really is the min and the max. We don't need the rmin and rmax, gmin, gmax, bmin and bmax. We just need min and max. The level that you get for the cube, you can make it so that it's the average between the min and the max, so that any pixel that falls between the min and the max goes to that level. The cube's histogram count, that we already know about the histogram, and what you're really doing is reclassifying those histogram elements. So let's think about this in a different way. Suppose you needed to create a range where we had something very similar to these elements in the range. I mean, that's kind of an interesting idea. Suppose we're inspired. Okay, let's say we're inspired by the median cut algorithm. So in that case, I would use a lower for a corner in the histogram, because we have a histogram, no question. An upper for another corner in the histogram. A count, that's still useful. And now the question would be, what should the cube's level be? And maybe what we can do is we can make this whole thing encapsulated by a refactoring. So that's very similar, except it's not a cube now, it's a range. So that's pretty cool. And then the question would be, how do you know how many ranges there'll be? Well, that's the k that's given to you in advance. Well, I guess it doesn't, you don't really need to have a separate thing called ranges. It's just an array of range. There'll be 256 ranges in the array of range. That's not a bad way to go. If you're following my thinking on this, all you really need is an array of ranges, because that's going to essentially allow you to cluster the histogram. So at the end of the day, when you're finished with this splitting, you're going to need an array of ranges, and there'll be 256 of them. So you could say range range array equals new range of 256. And now your goal will be to populate these ranges. And the ranges will be the min and max from each one of the median splits that you arrive at when you go through the array iteratively. So populate, here I'll put in a note, and I'll send this out as an email. Populate the range array to cluster the intensities into 256 ranges. Then classify each one of the pixels using a lookup table. Right? So what will happen is you'll have a lookup table that effectively will map the input value into an output value. It's like a hash table. So your lookup table is going to have 256 different values, and whenever a value comes in to a specific range, yeah, I mean the lookup table is going to be like this. Short LUT of 256 well, actually it's got to have an input which equals the number of input colors that you have. So we're going to have 65,536 input colors. Let's see, how many colors will there be? Equals new short of 65,536 different possible colors, and they're going to map into, each one of those values is going to map into one of the range buckets, and each one of those range buckets is going to be used to classify the color into one of 256 different possible values. So what you might do is, I'll give you a sample. LUT equals, well, let's see, LUT of 0 might be 0. LUT of 1 might also be a 0. Then you could say slash slash dot dot dot. By the time you get to LUT of, let's say, 355, well, that might map to a 255. And an LUT of, let's say, 350 might also map to 255. So then here it would say dot dot dot. So what you're doing is you're taking the values and you're using them to decide which buckets they're going to map to, so that you can get new values out that always range from 0 to 255. Because what you're really doing is you're taking numbers that have a higher dynamic range and you're mapping them into a set of numbers that have a lower dynamic range. And at the end of the day, you're going to have an 8-bit image. So then when you do your classification system, you're going to have to decide how to structure the lookup table over a variety of different ranges so that they map into legitimate numbers for an 8-bit image. Well, if you think about it, you're creating a function. And the function says if you have a number that ranges from 0 to 65,536, and you want a new number that ranges from 0 to 255, you have to map from one number into another set of numbers. So the lookup table does that mapping for you. It ends up being an efficient way to compute a function. So all you're really doing is you're saying LUT is really just f of x, where x is equal to your input value, and f is going to give you your output value. And the output value has to range from 0 to 255, and the input value apparently ranges from 0 to 355. So the question then is, how will you arrive at that mapping? And the answer is, well, if you use the median cut algorithm, you take the boundaries from the min and max, create a box, that's your range, and then you keep recursively subdividing the box in accordance with the number of pixels that are there that you've sorted. And so that's what the median cut algorithm is doing for you. What do you think of that? You know, when you looked at the homogeneous point processing chapter, right, there was a thing in there about how to do a lookup table invert, right? So if you looked at, for example, the lookup tables and the transforms for, let's see if I can find a good one. Yeah. So if you looked at homogeneous point processing functions, page 69, you saw there was a way to create a lookup table that said, look, if you got a 255, you return to 0. If you got a 0, you return 255. So the lookup table essentially said the function of the value is going to be equal to 255 minus whatever the value is, and we called that inversion. And so that gave us an inverse image. So that was how we formed the lookup table. You see. I think it's in, where did I leave that? It's on one of the filters under HPP. So if you look at that, yeah, here's the invert filter. Right? What does the invert filter do for me? Well, he gives me three functions for red, green, and blue called invert. And what it does is it says 255 minus v is going to give me the invert. And so then you say, okay, great. How does that create some sort of a processor? Well, it takes the invert filter and passes it into the homogeneous point processor filter image processor. And what that does is it creates a lookup table for red, green, and blue. So those are three separate functions, 256 elements each. And each one of those functions gets populated by the same get RGB implementation in the homogeneous point process lookup. And so then I do a lookup with my little image processing lookup table, and that allows me to map one value into another value. So what I did when I ran the function, which was a relatively simple function, is I traded CPU time for a memory lookup. And you might say, well, the memory lookup is slower, but in general the function could be arbitrarily complicated. So when populating the lookup table, you could, in theory, make things much faster if, in fact, that function were something other than a trivial subtraction. So the lookup table's got some optimization hacks associated with it, which we don't have to care about. But the key point is that all you're doing is you're taking one value and mapping it into another value.
How do we determine what those values are?
Using the median cut algorithm. So when you started with the minimum and maximum on the range, right? Then you formed the median, and then you proceeded to split the array. And you got two arrays. Now you got two different ranges. You can continue to split the array, and as you split the array, you split it into 255 different chunks. And so then once you get your 255 different chunks, you can have 255 different ranges. And those ranges,
Calculate for each one. You have to calculate the range.
yeah, you're going to have 255. So basically, the splitting will occur in 255 different times. Then you'll have 255 different ranges, and then you'll have to get the new value from each range so that it comes between 0 and 255. So probably each range will have a value that ranges sequentially from 0 to 255. And then you'll have an equal number of pixels mapping to each color. If that makes sense. I don't know if it's making any sense. I suppose we could do it by hand, but we ran out of time, so I got to get out of here.
Quick question.
Yes, sir.
What do you want as the output for this? Do you want a picture? Do you want the picture?
Yeah, I'd like to see the picture. I would like to see the picture.